Okay folks, we're back with our minimum spanning trees ideas, and we're looking at a second greedy algorithm. It's called Prim's algorithm for finding a minimum spanning tree. Okay, so like Kruskal's algorithm, Prim's algorithm is also greedy. It starts with an empty spanning tree. The idea is to maintain two sets of vertices. The first set contains the vertices already included in the minimum spanning tree as we obviously trace it out. The other set contains the vertices not yet included. So every step, it considers all the edges that connects the two sets and picks the minimum weight edge for these edges. Okay, so you choose an edge, then you choose a next, then you choose a next, and that choice is based on the minimum weight. Sorry. So after picking the edge, it moves the other endpoint of the edge to the set that contains the minimum spanning tree. So, okay. A group of edges that connects two sets of vertices in a graph is called a cut of this graph in graph theory. So at every step of Prim's algorithm, we find a cut of two sets. One contains the vertices already included in the minimum spanning tree, and the other contains those that we haven't used yet. We pick the minimum weight edge from the cut and include this vertex in the minimum spanning tree set. Okay, how does it work? Well, it says the idea behind Prim's algorithm is simple. It's a spanning tree. That means that all vertices has to be connected. So the two disjoint subsets discussed above of vertices must be connected to make a spanning tree. And they must be connected with a minimum weight edge to make it a minimum spanning tree. Okay, so how does the algorithm work? We create a set, we call it MST set, that keeps track of vertices already included. You'll see how we do that now. We assign a key value to all vertices in the input graph. Initialize all key values as infinite. Okay, we're not really going to follow that so strictly. Assign a key value of 0 for the first vertex so that it is picked first, while the minimum spanning tree set doesn't include all the vertices. We pick a vertex u, while not there in the MST set that has a minimum key value. We include it in the set. We update the keys every time we put in a new edge in our set. Okay, so I think, and we continue so until we've included all the edges in our minimum spanning tree. So let's have a look at how that is going to work. Now I'm going to do two things here. I'm going to use Prim's algorithm, and then I'm going to go back just to use the adjacency matrix again, so that you can get some practice and see how the adjacency matrices does exactly the same thing. Okay, so let's pick a node to start from. A clever one to pick is C, because C has two minimum weights running from it. Okay, so we're going to visit vertex C. Now remember, there's 1, 2, 3, 4, 5, 6 vertices. So we need 5 edges at the end of the day to have a minimum spanning tree. Okay, so let me get a color highlighter. We add C. Now from C we can go to F. Okay, so we have visited F. That's a weight. Let's keep the weights here. That's a weight of 2. Okay, then we choose. Okay, we're back. So we've recorded CF. We started at node C, went to F with a weight of 2. Okay, now we go back to C because we see there's another weight of 2 that we can rely on to create the minimum spanning tree. So far we've used C, F and B. Okay, now if we're back at F, we can now go one of two ways. Look, we need to get to A, we need to get to D and to E. So I can get to A quite quickly by just going from B to A. I could have gone from C to A if I wanted to, but that's a weight of 4. Okay, so far we've visited 4 vertices with 3 edges. Now we need to get to D and E. And it really doesn't matter how we get there, because this is a 3, that's a weight of 3. This is a weight of 3, that's a weight of 3. Okay, if there was a shorter way to go there, we could have chosen it, but it really doesn't matter. So we would have then visited the vertex E and then finally vertex D. So we have 3 plus 3, that gives us 10, and the weight of this minimum spanning tree is indeed 14. Now let's do the same, and so we're going to do the same problem, and this time we're going to do it with our adjacency matrix. Now let's form our adjacency matrix. It's a square matrix, A, B, C, D, E, F over there, and then A, B, C. Let me just make space here for us. D, E, F. Okay, so there we have our adjacency matrix. We are now going to populate it. So from A to A it's 0. From A to B there's a pathway length 4. From A to C there's a path length of 4. There's no other path length that runs between those 3 vertices. So we have to copy that row down as a column. B to B I have 0. So B to C, from B to C there's a weight of 2. From B to D there's no path. From B to E there's no path. From B to F there's no path. So we take this row and we copy it down into this column. Okay, C to C is 0. C to D, from C to D we have 3. From C to E we have 4. And from C to F we have 2. So this row gets copied down as that column. 4, 2, 0, 3, 4, 2, 4, 2, 0, 3, 4, 2. We pretty much do it because C and D and D and C needs to have the same entry. Okay, so there's a 0 over there. Between D and E there's a pathway of length 3. Between D and F there's no pathway. So D only connects to C and to E. You can check yourself. Okay, so 0, 0, 3, 0, 3, 0, 0, 0, 3, 0, 3, 0. I've got a 0 over there. Now between E and F there's a pathway of 3. So between F and E there'll be a pathway of 3 and there'll be a 0. Now if I draw in, or I just highlight my diagonal for myself so that I know I'm working either above it or below it to find the minimum spanning tree. So that's my adjacency, that's my adjacency matrix. Okay, so I'm now going to use this adjacency matrix and I'm going to find the minimum cost spanning tree over here. The smallest we've got is 2. 2 connects B and C. So definitely B and C, that is in. Okay. Then we have another 2 here that connects C and F. So C and F will be part of my minimum cost spanning tree, or my minimum spanning tree. The next is the sets of 3. There's 1, 2, 3 of them. Okay, so let's go for the first one, C to D. Well, C to D is that one, so I haven't formed a circuit yet, so definitely that will be in. D to E is another 3. D to E, I haven't formed a circuit yet, so definitely that is in. Now the only vertex that I haven't visited is the vertex A. I can get there from C or I can get there from B, and both of those have a path length of 4. So I'm just going to pick one. I'm going to go from A to B, and there's my minimum cost spanning tree. It's got 1, 2, 3, 4, 5 edges in it, and it has 1, 2, 3, 4, 5, 6 vertices. So the weight for this one is going to be 4 plus 2 plus 2 plus 3 plus 3. So that gives me 10 plus 4, which leaves us with a result of 14 for our minimum cost spanning tree, or our minimum spanning tree, using our adjacency matrix. Okay, I've got one or two more for us to look at. Now you'll see our weight with the previous one we did was also 14. Okay, so we're going to look at this diagram now. And we'll do both for this one, because it looks a little bit more challenging than what the others were, because there's more edges to it. Okay, so we're going to start and pick an edge. We're using Prim now. Okay, so it makes sense to start with this edge. Okay, so we've visited 7, vertex 7 and vertex 6. The weight we have so far accumulated is 1. Okay, now we're at 6 or we're at 7. Well, at 6, there's a side that helps us get to 5, which is a minimum side. So we now have visited vertex 5, and we've added a weight of 2. Okay, so now we can either go back to 7 and check, we can go to 6 and check, or we can go to 5 and check. Now from 5, it seems like the shortest one that we can then take is that edge that leads to vertex 2 and has a weight of 4. Now, at vertex 2, we can now come down and visit vertex 8. Okay, so that's a weight of 2. Okay, so from 5 we must visit 3 and 4 still, or from 2 we must visit 1. From 8 we cannot visit 7 because that will form a cycle. Okay, so yeah, we have to exclude this side. There's another way to do this. So we go back to 7, and we can see that if we go to 0 and 1 we have 12, or from 2 to 0 we also have a pathway of 12. So it really doesn't matter which ones we take. So I'm going to take 1 and then 0. So we visited 1 and we visited 0. So that adds a weight of 8 and a weight of 4. We could have gone 0 to 1 because the weights were the same. Okay, now please check this. If we had gone from 7 to 1, we would have used 11. And then to 0, it would have been 15. So that 12, or this 12, is still less than the 15. The only two vertices that we haven't visited yet is 3 and 4. Okay, so let's choose. If we go back to 5, we're going to have 10 here. So I suggest we go to 2 and we visit vertex 3. Okay, having done that, we've added a weight of 7. And then you really just have one choice left, and that is to go to vertex number 4 with a weight of 9. Now let's just see. There's 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 because we started at 0. Okay, so if there's 9 vertices, there must be 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. So indeed, we have used Prim's algorithm correctly. So to calculate this weight, we've got 10, we've got 19, we've got 29, 30. Our weight is 37 for this particular graph. Okay, that's using Prim. Let's go and use our idea of an adjacency matrix. There's vertices again. Let me just move and make space for us. There's vertices 0, 1, 2, 3, 4, 5, 6, 7, and 8. There's 8 vertices there. Starting at 0 is actually 9. So our adjacency matrix is the square 8 by 8 matrix. 0, 1, 2, 3, 4, 5, 6, 7, and 8. So I'm going to try and squeeze it in here so that we see all of it. Okay, so let's see. From 0 to 0 we have a 0. Then from 0 to 1 there's a pathway with weight 4. From 0 to 7 there's a pathway of weight 8. Covering 0. 0 excuse me, only connects with 1 and 7. So the rest of this row will be filled with zeros. There's a 4 here. The second last one has an 8. The rest of this is filled with zeros. Okay, then we record a 0 and 1, 1. Is there a pathway between 1 and 2? Yes, it is, and it has a weight of 8. So between 2 and 1, we'll have that repeated. Is there a pathway between 1 and anything else? Yes, 1 and 7. So between 1 and 7, there's a pathway of 11. So between 7 and 1, we'll have a pathway of 11. So 1 connects with 1, 2, 3 vertices. 1, 2, 3. We've recorded them. So let us fill the rest of this with zeros. Okay, we go to 2, 2. We record a 0 there. 2 connects to 3 vertices. 1, 3, and 8. So 2 connects with 1, with 3, with a weight of 7 there. So the weight 7 here between 3 and 2. And also 8 with a weight of 2. So 2 and 8, and 8 and 2 connects. The rest of them, there's no connection. So as per the definition, we record zeros. Now you can check yourself. 2 connects to 3 vertices. So there must be 3 weights. So 3 and 3 is 0. Okay, 3 connects to 1, 2, 3. It connects to 2. 3 connects to 2 with a weight of 7. We've already recorded that. 3 then connects to 4. 3 to 4 with a weight of 9. So 4 to 3 will have a weight of 9. And then 3 to 5 will have a weight of 14. So 5 to 3 will have a weight of 14. And that's it. Now check yourself. 3 has connected to 1, 2, 3 vertices, 1, 2, 3 entries. Okay, 4 and 4 is 0. 4 connects with 2, with 5, and with 3. 3 is already in as a 9. So we can now say 4 connects with 5 with a weight of 10. A weight of 10 there. So 3 zeros here, 3 zeros over there, and a 0, 0 here. Then we go to 5. Now 5 connects to 1, 2, 3, 4 vertices, of which we've already got 2 in. So 5 connects to 6 with a weight of 2. 5 connects to where? To 2 we've already got. 5 is connecting to 3. Let's go slowly here. 5 connects to 3 with a weight of 14. Cool. 5 connects to 4. Where's 5 connects to 4 with a weight of 10? We've got that. 5 connects to vertex 2 with a weight of 4. So we filled in 2 and 5 with a 0, but 2 and 5 actually should have a 4. So 5 and 2 must also have a 4, because there is definitely an edge connecting them. It was a silly oversight. So 5 to 7, there's nothing, and 5 to 8, there's nothing. Okay, so what do we have? We have 1, 2, 3, 4 connections. Let's just check. 1, 2, 3, 4, perfect. The rest are zeros. So 1, 2, 3, we must bring down, let's just bring down the column 004, 14, 10, 004, 14, 10, 0. Okay, and then we have 2 and 2 zeros. You can see your eye starts going squint when you start working with so many entries. Then we go to 6 and 6, we record a 0. 6 connects to 3 vertices, while 5 is lower than, so we only need 2 entries. From 6 to 7, from 6 to 7 it's 1, so from 6 to 7 here we'll have a 1, and from 6 to 8, 6 to 8, there is a weight of 6, so there's a weight of 6 here. Okay, there's a 0 there, so what does 7 connect to? 7 connects to 8 with a weight of 7, a weight of 7, and there's our 0. Okay, so let us now use the very same adjacency matrix, and I'm just again going to highlight, my eyes go quite funny with all these entries. I'm going to highlight that diagonal so that I can start at the top. Okay, the lowest edge is the 1 down here. 1 connects, let me use another color because we've already used green on there. So let me use the blue. 1 connects 6 and 7. So 6 and 7 is definitely part of our minimum spanning tree. Okay, remember we are avoiding circuits. Okay, so the next number will be 2 there and 2 here. 2 connects 5 and 6. 5 and 6 is connected by a 2. So there we go. That's part of the spanning tree. And 2 and 8. Vertex 2 is connected to vertex 8 with a weight of 2. So far, no circuits formed. So we can either use 6, 4 or 7 depending on what comes next. So we've got 1 and 2 used. Our next number, our next highest number is 4 up there. 4 connects 0 and 1. So if I go from 0 to 1, I have a 4 that lies there. There's no circuit, so perfect. I have another 4 at 2 and 5, the one we missed initially. Okay, so between 2 and 5, I have another 4, so 2 and 5, that is included. Okay, so I can't use 6 or 7, because that's going to form circuits. Okay, so 6 is going to go away and become a 0 here. So 6 and 8, I can't connect. And what's the other one we said? And 7, which is 7 and 8, I also can't connect them. So far I have visited 1, 2, 3, 4, 5, 6, 7 vertices. Okay, so we've last ended at 6 and then 7. Okay, so after 7 we go for 8. So let's go for 1 and 2. 1, vertex 1 and vertex 2 is connected by an 8. And then there's another 8 between 1 and 7. 1 and 7. Where's my 7? Where's my vertex 1? Vertex 1 and vertex 7 has an, what am I saying here? It's vertex 0 and vertex 7 that has the 8 at the top. So here's 0 and 7. Do I have any cycles? Oopsie, you can see I just formed a cycle there. So I'm not going to use this one. So that I'm going to take away, and it's going to become a 0. Okay, so far I have visited 0 and 7 in any case, so I shouldn't have even gone there. Now I have to visit, I've visited all of these, I need to visit 4 and 3. The quickest way there will be, let's see, if I take the next highest number, which will be this 7, to get from 2 to 3. There we go. And then I can go to 4 with the next highest number, which in this case is 9. Connects 3 and 4. So there's my minimum cost, or my minimum spanning tree, using an adjacency matrix. So the weights will be 4 plus 2 is 12, 11, 12, 13 plus 9 is 22, and then the 3 down here gives me 737 as a minimum weight. And that's exactly what I got when I applied Prim's algorithm. So folks, there's a few things to remember. To find a minimum cost spanning tree, you've got Kruskal's algorithm, you've got adjacency matrices that you can use, or you can use Prim. Know all 3 of them, because we're going to ask you to use one of them to find minimum spanning trees. Okay folks, if you learned something about your graph theory here, please like the video, and also don't forget to subscribe to my channel.